So learning objectives for 1-5. And 1-5, if you were peeking at that before I got started yakking here, we're talking about inverses. You did inverses in Algebra 2, so it won't be totally brand new. And we have 4 concepts to rate yourself before the lesson. I can determine if a function has an inverse function. Yeah, we actually have a test for that we talked about last year in Algebra 2. I can find an inverse function algebraically and graphically. I can prove algebraically that 2 functions are inverses of each other. And I can determine any domain restrictions on the original and the inverse function. So we've got 4 of them listed on here. Kind of think back, and you remember some of that stuff? Talking about inverses, does it come back a little bit? Because obviously, you know, everything we do at the pre-calc level is Algebra 2 on steroids, so it's a little bit deeper and a little bit harder than what you saw last year. And then usually there's a new twist to it. And I would say, you talk about domain and range of inverses at the Algebra 2 level, but it's so brief. You maybe spend 10 minutes talking about it in class and have 2 or 3 problems on the homework. So that one, that might have just flown out of your ears by now. You know, it's one of those things. But the rest of this, as we do it, I think you're going to feel like, oh gosh, this is a lot of review today in section 1-5. So, away we go. We talked yesterday about how a relation is anything at all that you can graph. So if you just made up a whole bunch of numbers and you grouped them into 2s for ordered pairs, groups of 2, that's a relation. And you can find the inverse for any relation. You just take the ordered pair AB, and like it says, you switch it around to BA. Then it's the inverse relation. So literally the inverse is switching the x's and the y's. And that's because to find an inverse, what we're really doing is we're reflecting over the line y equals x. And when you do that, those 2 switch positions. So a's become b's, x's become y's is probably more along the lines of how we want to think of it. And then we get to something that we already know how to graph. Our little parabola here. Way back when you were in pre-algebra, they would have said, let's put like -3, -2, -1, 0, 1, 2, and 3 into these functions if we've never seen them before. And then because it's y equals x squared, we square those. And we got used to that as the parent function for quadratics. You know, it doesn't have any other numbers. It's just y equals x squared. That's your most basic parabola. And we graph that. And of course, you talked about symmetry and how you could transform these vertical stretches and compressions, shifting it right and left, up and down, making those translations. But now what we want to do is look at, what if they say graph the inverse function? And we don't want to go through the trouble of reflecting everything over the line y equals x. Well, we don't have to. All we have to do is literally switch the x's and the y's. That's all we have to do. So I take this list of y's and I put it over here for the x's. And I take all of my x's and I put them over here for y's. And we just switch the x's and the y's, which means we are swapping the domain and the range. And then we graph those. And basically it just looks like we took it and turned it, you know, that we rotated this 90 degrees about the origin to get our new relation over there. But in actuality, it is literally a reflection over the line y equals x. And just to remind everybody, the line y equals x goes through 1, 1, 2, 2, 3, 3, etc. perfect diagonal through first and third quadrant. So it makes sense that if we reflect this, it's going to come down here. I mean, just thinking about that equal but opposite reflection that has to take place. So now, what we want to talk about, and I've talked about this all the way through, we like to have functions. If we have functions, there's a lot of math we can do at the calculus level. So when I look at the original and I think about my green one up here, I realize, well, that's going to pass the vertical line test. Yeah, that's going to be a function. But if I try to use the vertical line test over there on my red one, major fail. You know, almost all the points it's going to hit in 2 spots. So that's a no. Now, like it says, could we have predicted? And if so, how? Well, kind of 2 ways. Because we know from Algebra 2 that there are 2 steps whenever you want to write an inverse. And those 2 steps would be switch the x's and the y's and solve for y. And when I solve for y here, I'm going to have to take the square root of both sides, and that means 2 outputs. So algebraically, we can know now that, you know, we're not going to get for the inverse. It's not going to be a function. But we had another test last year, too. Didn't use it a whole lot. Like I said, it's one of those little blurbs, and you do 10 minutes of homework, and you're done. And that's the horizontal line test. The horizontal line test says if we draw a horizontal line anywhere on our original function, and it passes through more than 1 point, then the inverse will not be a function. So 2 ways. We could look at this algebraically, or graphically. I've got 4. I might have had to just stand here and talk to myself instead of teaching you guys the video today. All right, so this one says the inverse of a relation is a function if and only if each horizontal line intersects the graph of the original relation in at most 1 point, which I just talked about, the HLT instead of the VLT, the horizontal line test. So this one is used to talk about the inverse, whether or not the inverse is going to be a function. So down here in example 3, it says we're going to apply that horizontal line test, and well, actually we're going to do both, the VLT and the HLT. So which of these graphs, 1 through 4, are graphs of relations that are functions? So let's just go through and talk about the vertical line test. And remember, these are supposed to have arrows on them, but that shouldn't affect the way we talk about them. So can I put down A for this one? Is this a function? All right. So if this one gets A, how about the second one? Is that a function? No, failing big time, right? How about number 3 here? Function? No. Number 4? Yeah, that one looks good. So those get the little A because those are originally functions. Now switch the way you think about it from vertical to horizontal. Can I put a B that the inverse is a function for number 1? Yes. How about number 2? Horizontal line test. Yeah, it looks like there'd be asymptotes there, so that looks good. How about number 3? Failure again, right? 4? No go. So visually, and this seems really silly, but on the MCAs, there's always one of those. Every year, always. And usually they just ask, is the relation a function? They don't even want you to talk about the inverse at all. So they want to know that you understand the vertical line test. That's the big piece for all of this. And it's a basic question, but that's why it's there. So they can know, hey, almost everybody in the state has gotten through that Algebra 2 level where they've talked about the vertical line test. So a function whose inverse is also a function is a really big deal. It has a graph that passes both the HLT and the VLT, such as that first graph that we just looked at in that example. And that function is called 1 to 1. And like I said, that's a big deal in calculus. Not only is the original a function, but its inverse is also a function. And like it says, every x is paired with a unique y, and it works backwards. Every y has a unique x. So, definition of an inverse function: if f is a one-to-one function with domain and range R, then the inverse function, we get a little notation of f. It looks like f to the negative 1, but that is how we write, how we annotate inverse functions. This is going to be a function with, notice how they swap. The range of the original becomes the domain of the second, and then the domain of the first becomes the range of the second. So, if they don't give us a new name for inverses, we have to use this. We do, because we have to show people that we understand this was an inverse that we found. It's just not another problem that we did that has y. It's an actual inverse. So, the inverse of b equals a, only if the original said that when you put in an a, you get a b. The x's and the y's, the domain and the range, swap positions. So, as we keep working on our list of objectives, our concepts here, now we want to find these. And again, there's two really basic steps. Sometimes it takes more steps than that, but the basic steps are, number one, switch the x and the y. And number two, get y all by itself. So see what you have and figure out how you can get it to say y equals. And then I would say for us at this level, there's that step 2.5 where we're going to be really careful about the name. If they tell us to give it a new name, h of x, g of x, whatever it may be, we need to do that. If they don't, then we need to use our inverse function notation to show that that's an inverse. So it's a little extra kind of thinking step there at the end. Find an equation for the inverse if f of x equals x over x plus 1. So the first thing we do is write this so it looks like a fraction instead of looking like computer language, and we use a y for f of x. So the function notation, we kind of have to throw that out the window so that we can see where the x and the y are. Then we switch the x and the y. And this is why I said that second step. Sometimes there's more steps you have to do to make that happen. I mean, we can't have what we're trying to solve for in the denominator. So the first thing we would do is either treat this as a proportion and cross multiply, or multiply both sides by y plus 1. Either way. And I realize, okay, y is not by itself yet. And there's some stuff going on here. I'm going to have to distribute that x so I can figure it all out about how to get y by itself. So xy plus x equals y. So now I need to get all of this taking place so that I just have y equals blah, blah, blah on one side. Well, to do that, I better get all the stuff that has a y on one side so I can figure out how to separate it. And this will say, and I'm going to run out of space, that's what I'm worried about here. I'm going to come up here. So I need that y all by itself. I do have my y's on one side now. So now I need to separate it from the rest of it. And to do that, I'm going to have to factor. And now, if I divide both sides by 1 minus x, I will have y in terms of x. And then I stop, because I need that step 2.5. What should I name this thing? Well, they told me. This one is just going to be f inverse of x. That's going to be our notation. And we've got it. Now, while I was going through that, I'm trying to think, did we give you any of that complicated in the Algebra 2 level? I think so. I think you saw like 1 or 2 of these in the homework if whoever you had decided to assign those. Because for most students at the Algebra 2 level, this would be a little bit too much. You know, there's too much going on. But I'm pretty sure you guys experienced a little bit of having to move things over and factor and all of that. So that's really not new. Might feel like it, but it's not. And then next up, still working on those objectives, finding an inverse function graphically. So what does it look like to do that? All we have to remember is it's as basic as the x's become the y's and the y's become the x's. That's what happens with an inverse. So the points A, B, and BA in the coordinate plane are symmetric with respect to, here's the big deal, the line y equals x. That's what we're reflecting over. The points A, B, and BA are reflections of each other across that line y equals x. That's how we get inverses. Now, the name inverse, typically when we talk about inverses when we're just solving, we're thinking, how do you undo something? So it's weird to think of this as an inverse, but it literally is how you undo a graph. You find its inverse. That's how you undo it. So example 5. Finding an inverse function graphically, the graph of the function y equals f of x is shown. Can't help it, I just had to do that. It says sketch a graph of the function for the inverse, and is f a one-to-one function? Well, let's start at the beginning. I need to figure out what the graph is going to look like. So the easiest and fastest thing to do is to find some nice points on this graph, and then just swap out the x's and the y's. So let's see, this looks like it might be -2, -4. That is definitely -1, 0, 0, 1, 1, 2, and then 2, it doesn't look like quite 4, so maybe I won't write that one down. I'll use those. So for its inverse, I swapped my x's and my y's. So I just graph the points from switching the x's and the y's. Oh, my negative doesn't look good there. If I'm going to put these notes on the internet, I better have it so they can read them. There we go. So with any graph, if we can just figure out, even approximate some good points on the original, all we have to do is switch out the x's and the y's, and we've got it. So finding an inverse function graphically, it's not supposed to be that difficult, but you have to know what an inverse is, and you have to know about the domain and range switching. So we sketched a graph, and then they want to know, is this a one-to-one function? So is the original and the inverse, are both of those functions? Yeah, this would be a one-to-one function. Again, we didn't have to graph the inverse to know that. I mean, it's kind of nice. The visual makes it super nice. But we could have used the horizontal line test on the blue one that's up here, and we would have known, yeah, the inverse is also going to be a function. So they're going to ask you some questions like that in the homework. Again, don't overthink it. Just think switch the x's and the y's. Domain becomes the range, etc. Now, this one scares people. Whenever you see the word prove, People can't help but have flashbacks to geometry and the two-column proofs. We don't do the two-column proofs at this level. We do use some paragraph forms of proofs. So you need to know that most of what we do at this level involves algebraic proofs. It's going to feel just like you're doing an algebra problem. It's not an actual proof. Sometimes we'll show you those in class, but usually your homework is just use the algebra that you know to make sure that this is going to work. So, inverse composition rule. I love this. This is just such a cool thing. The function f is 1-to-1 with inverse function g if and only if. Now you look at this and you see, oh, they're going to do composition both ways. But this is what's fabulous about this process. If they are truly inverses, it doesn't matter which way you do the composition. Your answer will be x. Here's the reason I love that. You know what the answer is. You know what you're working towards. So not only do you know what you're starting with, but you know what you're supposed to get at the end. If you don't get x, well, either you miffed it or the inverse isn't a function, because that's the only way that we can check to see, are they both functions? So this one, I know you didn't do any that were this complicated. Oh, for the extra example, you saw some of these. You did do things like this. This is verifying inverse functions up here. It says show algebraically that f of x equals x cubed plus 1 and g of x equals the cubed root of x minus 1, that those are inverse functions. Now, this is a really important step. You have to write down which way you're going to do it. You can't just dig yourself into the math. So you have to realize, hey, I have to show this in both directions, because composition is not commutative. It's not always supposed to work in that reverse order, but it's supposed to if it is a one-to-one function. So what this says is I have to take g of x, and wherever I see x and f, I have to replace it with this. So this is going to go right there. So this is going to say the cubed root of x minus 1 cubed plus 1. Now, you have to show each step. Pretty obviously, like I said, we know what the answer is. You can't just write down x and walk away. You have to show, oh, look at that. Cubed root and cubing. Those are inverses of each other. That's a step. Oh, look at that. Negative 1 plus 1. Gone. So the important part of these problems is that you're showing those steps of things dropping out, and you're not trying to do 2 or 3 steps at one time. Each step is, hey, I did just this one thing. Now I did just this one thing. Too many students try to skip things and go directly to x. That's silly. We already know what the answer is supposed to be. You're supposed to show us what are the steps that got you there. Now in reverse, take f of x and put it into g. This will go right there. Bless you. Hopefully the first obvious you see is, oh, plus 1 and minus 1, for goodness sake. Oh, look at that. They're inverses of each other. It's not that it's difficult. It's just that you have to show those individual steps. No skipping a step. No doing 2 or 3 at one time. And there it is. Now, I hate to tell you this, but that was an easy one. This next one, a little more complicated. So, our extra example says, let g of x be the inverse. Now, I'm going to underline that because remember, that's step 2.5 is you give it a new name, and I don't want to forget that. So here it is, and it's a pretty complicated looking cube root graph there. And it says for a, let's just figure out what g of x is. All right, well, g of x is the inverse. So I'm going to write this with a y in it. And then I'm going to follow those 2 basic steps. Switch the x and the y. And solve for y. Okay, so I'd have to add 5 to both sides. Then I'd have to divide both sides by -2 because I have to isolate my radical. Oh my. Then I'm going to have to cube both sides. I've got to get rid of that radical. So now in this step I start to think, okay, I don't want to figure out what x plus 5 times x plus 5 plus times x plus 5 is. Obviously that would not be a simplified form. But I definitely know -2 times -2 times -2 is -8. So that part I can simplify. And last but not least, I need to move over the +1. And give it that step 2.5. This was supposed to be g of x. That's too squished. All right. So now, where this becomes challenging is, remember what we're going to do with this. This big mess has to go inside that other big mess up there, and vice versa. So, try to think of the x as just a slot that has to be filled. As we go after b, oh, I better not use blue, used that before, g of f of x. And I always encourage students to write it with the parentheses instead of writing it with the little bubble, the composition bubble. And that's because it gives you that feel of, okay, so I have to take f of x and put it inside g of x. I mean, that's exactly what's happening here. So, this monster is going here. Give yourself some space. It's a lot of stuff. I think I got it all. Scrolling up and down does not help with these. So far, so good? Okay, something obvious that knocks out right away. The 5s. Something that might take a second's worth of thinking is cubed root being cubed, right? And the one thing you have to be careful of is the fact that the -2 is also inside there, so that also has to be cubed. I better not lose my equals here. Then what's going to drop out? -8s are gone. And, of course, we get down there and we're like, oh, yes, that's exactly what was supposed to happen. Woohoo! We did it! Not difficult, but complicated, if that makes sense, right? Because there's a lot going on, but it's supposed to just drop out, drop out, drop out, drop out, and boom, you're left with x. And now, the opposite direction. F of g. So now we're taking this monster fraction and putting this under a cube root. Wowzers! All right, I scrolled up, so I'm going to have to use this. Whew. Obvious first dropping out is what? +1, -1. Well, I better try to do something with all that cube root and cubing stuff. Those are inverses of each other. So -2, and then we'll have x plus 5 over -2 minus 5. Obvious next step would be? Or is it not so obvious? Yeah, // do your strike. And woohoo! We did it! Complicated, not necessarily difficult. So this one definitely a step up from what you were doing in Algebra 2, but it's good to see it again and know that even with the more complicated ones, yeah, this is definitely going to work. You just have to hang in there, you know. It's more about organization than it is about being able to do tough math, you know. Keep it so you can read it and follow everything. Now, since there was so much in there, if this is on a test, I'm going to double check. Okay, did I remember to call it g of x? Yes, I did. Did I do parts A, B, and C? Yes, I did. Because one of the things I've noticed on the tests that we've been taking is sometimes people are messing up because they didn't read the problem enough, you know, what they're supposed to do for all parts of the problem. So this would be a time to slow down a little bit and make sure you've got everything you need. All right, this is never anybody's favorite part of talking about inverses. And that's the part of our objective where we talk about restricting the domains. Determine any domain restrictions on the original and the inverse function. So like it says, we often need to study the inverse of a function. It's not one-to-one, but we need to study it. We need to be able to do the math. To do this, we simply need to restrict the domain and look at only part of the original function, which I mentioned in yesterday's notes. So, y equals x squared. It's huge. Put a negative in front of it, and you have the path of anything that's thrown into the air. We have to do calculus on that. It's a part of life. It's a part of gravity. So, we're not going to be able to take the whole thing. Because if we did that, this is going to fail the horizontal line test. So usually, if it's real life, real world, we're going to take the positive side of the graph. And we'll say, you know what? I'm going to make sure that my domain is from 0 to infinity. And then my range is also going to be 0 to infinity. And I only look at that portion of the graph and the inverse of only that portion of the graph. So when I do my inverse, that's the part I study, which will have a domain from 0 to infinity and a range from 0 to infinity. It just kind of swaps them out, even though with this one we can't see that because it ended up being the same. So if we just look at one side, like the right side here, from 0 to infinity, that inverse will look like that. And if we put the arrows on here, we will recognize that graph because it's the inverse of squaring, which is square root. You know, we'd switch the x and the y, and then we'd take the positive and negative square root. But because the domain is restricted, we would only use the positive. So it's the graph of y equals the square root of x. It's our square root function right there. So now we have to think, okay, if I have to restrict the domain, that means I have to think about what happens with the domain and the range for my inverse, that those two swap out. So how to find an inverse function algebraically? Don't forget, name it F inverse using the F inverse notation if they don't tell you a new name for it. Determine that there is a function that is the inverse by checking that it's one-to-one. So vertical line test, horizontal line test, or switching the x and y and solving for y to see that you get one output. Then state any restrictions on the domain, like in the last one, we couldn't use the whole thing. Note that it might be necessary to impose some restrictions, to say, hey, only use this part of the graph. Here's my new domain, my new x's. We want that one-to-one version. Switch the x and the y in the formula, solve for y, make sure you use the new notation, and state any restrictions on the domain of the inverse. If you have to restrict the domain for the original, then you have to talk about restrictions again when you get to your inverse. Show that f of x equals the square root of x plus 3 has an inverse function, and find a rule for that inverse. State any restrictions on the domain of f and f inverse. Okay? So far we have f of x equals the square root of x plus 3. And I know I have to restrict the domain for that one because we're staying in the real number system, and that means x plus 3 has to be greater than or equal to 0. So I'd have to subtract 3 from both sides. And that means my domain of f would be from -3 to infinity. And then I think about what that means for the range of f. Well, if I want to find the cutoff for the range, all I really need to do is put in this first number that I restricted to know where it's going to start. -3 plus 3 is 0. The square root of 0 is 0. So my graph is going to start at 0, and it's going to go up because this is positive. So now, before I even do the rest of this, I'm going to come over here, and I'm going to make sure that I write that the domain of the inverse of x will be from 0 to infinity. And the range of f inverse of x will be from -3 to infinity, because the domain and the range have to swap. They have to. Now, algebraically, I'll figure out what will that inverse look like. So that means I have to make my f of x a y. I have to switch the x and the y. Going to have to square both sides. And then I'll have to subtract 3. And finally, I can't leave it y. This is special. This was the inverse of this function. They didn't give me any fancy names, so I'm going to say f inverse of x. And hopefully you can't help it. You're like, oh, I know what that looks like. That's a parabola with a vertex down there at 0, -3. It is, but remember we can't use the whole thing because this was only a positive square root of x plus 3. Those are spaced out too far. So, my domain restriction was I can start at 0 and I can go to the right forever. So it would start down here at -3. And then, since it doesn't have any vertical stretches or compressions, normally from the vertex we'll go right 1 and up 1. And normally from the vertex we would go 2 to the right and 4 up. And you can go back to the table we made earlier to see that, the squaring function. So that is my inverse. But I also want you to see the original, because I think it's powerful to see that reflection in the line y equals x. So our original was that square root of x plus 3. So that starts back here, 3 to the left. And since that's our square root function, it would be 1 to the right and 1 up, 4 to the right and 2 up, and we can see why those domain restrictions work with this one. This was the positive square root of x plus 3, so we only receive the top portion, this black curve up here. And then this is our inverse, which of course reverses the domain and range pieces that we had, which it should, otherwise we messed up. You know, that's how it's supposed to work. So we do this algebraically. We can graph to kind of double check and make sure, yes, it looks like everything's been reflected over line y equals x. And we just plowed our way through all of those objectives. So we've talked about all the pieces that we need to with our inverses here. Did you get a feeling like I know how to do this, I've done this before? Okay, good. So some of that was coming back to you as we went through this. But there's 1.5, and tomorrow we must have had at least 2 days on 1.6. Can't imagine we tried to get through that. Yep, so tomorrow will be 1.6 day 1. Next week we'll come back and finish up. And we will have a test, and it's going to be on a Thursday. So this will be one of those times when you guys are taking the tests on the Thursday when it's supposed to be taken. And the other group, they have to wait until they come back on Monday. But it happens. We do what we got to do in this weird time.